Hello everyone and welcome to Waves. So this is just going to be a quick video talking about some of the common characteristics of waves and how they relate to one another. So whether you're talking about water waves, light waves, sound waves, or any other kind of wave you can think of, all waves share some of the same characteristics and all of them behave in a similar way. So to demonstrate this, I'm going to bring up a wave here. We can see we have here a red sinusoidal wave, and you can see that it's traveling towards the right. If you were to ask how fast it's traveling, you could say it's traveling with a velocity, which we give the symbol v, and we measure that in meters per second. You're probably familiar with velocity from other contexts. The other thing we can see straight away is that our wave is moving the medium that it's traveling through up and down. How far is it moving up and down? We call that distance the amplitude. We measure it in meters because it's a distance. The thing to be careful with the amplitude is remember that you're measuring from the central position, the equilibrium position of the medium that it's traveling through. And so that's commonly going to be the middle of the wave, and we measure it up to the top of a peak or to the bottom of a trough. Just be aware that you don't measure from the top all the way to the bottom. That's double the amplitude. The next thing I want to talk about will require us pausing animation, so here we go. With it paused, we can see that this is just like we've taken a snapshot, like a photograph of our wave, frozen it in time, and you can see it repeats itself over and over again. The distance it takes to repeat itself, we call the wavelength. We give it the symbol lambda, which is like a Greek letter L for length, and it's a length, so we measure it in meters. We could measure it, as we have here, from trough to trough. We could measure it from peak to peak. We could also measure it from the start here in the middle to the point where it repeats itself again. Just be careful not to measure half the period. You can see this point here is returned to the middle, but it's going downwards instead of upwards, so just be aware of that. The next thing I want to talk about focuses on the actual particles making up the wave. So I'm going to bring up an arrow here, and you can focus on this particle here, what its motion is going to be after we start moving the wave again. So I'm going to predict, you can see here, as the wave moves to the right, the particle that's here is going to have to move up and then down again. So to graph this out, here's a set of axes. Watch carefully this point here. You can see it goes up and then down and up and down and up and down and so on and so forth. So you can see here it repeats itself over and over again. The motion of the particle repeats itself over and over again, just like the wave itself repeats itself over and over again in space. The difference, of course, here is that we're measuring in time, not distance. The time it takes for our particle to repeat its motion is called the period. We can measure that again from peak to peak or trough to trough. We give it the symbol capital T, and it's measured in seconds. It's just a time. This is quite a natural way to measure how fast the wave is moving. If you're at the beach, you're bobbing up and down, a wave washes over you, you're interested in how long it takes for the next wave to arrive. However, for a lot of the kinds of waves we're looking at, sound waves and light waves, they have very, very short periods. They repeat themselves over and over again, many, many times in 1 second. In that case, it's probably more natural to talk about the frequency. We give the frequency the symbol F, and we measure it in per seconds. It's how many repetitions per second does this wave have. Per second or reciprocal second or something like that is sort of a bit of a mouthful. So we actually give this per second unit its own name, the hertz. And we give that the symbol Hz. Now you might find yourself wanting to convert between period and frequency. They're both kind of measuring the same thing. That's actually quite easy. You just use the formula down here. Frequency is equal to 1 on period. Or alternatively, period is 1 on frequency. Now that we've got all these characteristics together, we might wonder how they relate to one another. So let's consider the velocity. How fast is this wave moving? Well, the distance it has to travel before it repeats itself once is 1 wavelength. How long does it take before it repeats itself? Well, we can see down here, it's 1 period. So we can put that information together. Remember that in time t, a wave travels a distance lambda. The velocity is given by the distance travelled divided by the time taken to travel that distance. So we can write that out just as v equals lambda on t. And it's common to see it written out like this. But if we remember that our frequency is equal to 1 on t, then we can replace the 1 on t in this equation with an f, and we get v equals f lambda, which is a more common way of writing this. So your velocity is frequency times wavelength. This is a really useful equation. I highly recommend you memorize it. It's just really common to get a situation where you know two of the elements of this equation, you know the frequency and you know the velocity. You want to find out what the wavelength is, or you know the wavelength and the velocity, so you want to work out the frequency. So I recommend just trying a few problems. Make sure you get this down. A lot of future wave type problems will rely on this equation. Okay, so hopefully that helps. Thank you for listening, and I'll be back with a new video soon.